A smartphone glows in a dark room. Its screen pulses, notifications, recommendations, reminders, all arriving with uncanny precision. You don't see the code driving them, but it sees you, and it decides more than you realize. If you're watching this, code already shapes your day. What you see, what you buy, what you believe. You've heard programming is the future. You've seen the job ads, the coding boot camps, the stories of overnight millionaires. Maybe you've even tried learning it, wrestling with loops and functions and error messages at 2 a.m. Or maybe you use its products every hour without noticing. But beneath the tutorials, the Silicon Valley myths, and the tech moguls lies a stranger story. A human story, one filled with obsession and rivalry, with accidents and ambition, with brilliance and blind spots. And these choices, made by people you've never met, still steer the world you move through. Consider what happens when code misfires. In 2012, 16 faulty lines triggered a $300 million stock market flash crash in under a minute. In 2018, a software system inside Boeing's 737 MAX pushed 2 jets into fatal dives. And in modern ICUs, a single device can hold more than 7 million lines of embedded logic, quietly sustaining life. Programming isn't just instructions for machines. It's the hidden architecture of civilization, the nervous system of everything built after the year 2000. The real story of programming isn't about computers. It's about people brilliant, flawed people, who built new power before they understood its consequences. So we'll travel from the 1840s to the AI-driven present, uncovering forgotten origins and the human dramas behind modern code. By the end, you won't just understand programming, you'll see the world differently. Chapter 1. Ada Lovelace and the Machine That Shouldn't Have Been Possible. Have you ever wondered how someone can write code for a machine that doesn't exist? How a person in the 1840s could imagine a future no one else could even describe? That question haunted a young woman in Victorian London long before programming had a name. London, 1843. Gas lamps flicker against a cold window. Ada Lovelace, 27 years old, intense, restless, scratches equations across ink-stained pages. She chases abstraction the way others chase adrenaline. She gambles, literally, building horse-racing algorithms that will cost her the modern equivalent of $250,000. But this night, she pursues a bigger obsession. Across the city, Charles Babbage storms through his workshop, surrounded by brass gears and half-finished dreams. Babbage, brilliant and abrasive, designs machines he never finishes. His analytical engine demands perfection. Investors flee. He refuses to compromise, burning through 17,000 pounds, more than 2 million pounds today, without producing a working model. When Ada and Babbage meet at a party in 1833, something ignites. He shows her a sketch of the engine. She sees something he doesn't. He sees machinery. She sees language, symbols, logic. She imagines looping instructions written on punch cards, an idea a century ahead of its time. Society calls it poetic nonsense. She writes anyway. Her vision becomes the first published computer program on a machine that exists only on paper. The problem? Without funding, the analytical engine stays theoretical. Ada's ideas disappear into archives, waiting for someone to rediscover them. And a century later, someone finally does, sparking a revolution no one sees coming. Chapter 2. The Codebreakers Who Turned Programming into Survival. What if the first people to truly program a machine weren't building software at all, but trying to stop a world from collapsing? What if code, in its earliest modern form, wasn't about efficiency or elegance, but about survival? Rewind to 1941. Bletchley Park, a damp English estate converted into the nerve center of secrecy. Inside Hut 8, electromechanical bombs 10-ton, beasts of steel and wiring thunder through the night. This is where the future of programming quietly accelerates under crushing urgency. Alan Turing works hunched over a wooden desk, fingers stained with graphite, mind sprinting miles ahead of those around him. He runs 40 miles on country roads to clear his thoughts, then returns to design logic diagrams that intimidate military brass. Turing speaks softly, stutters slightly, but his ideas detonate on impact. Across the room sits Joan Clark, a cryptanalyst paid less than her male peers, denied promotions she earns with raw brilliance. She dismantles ciphers in silence, building chains of deductions that reshape Allied strategy. Their enemy is Enigma Germany's encryption system, updated daily. Humans need years to brute force a single key. Turing's bomb completes the same work in 20 minutes. But early proposals meet resistance. British commanders dismiss his abstractions as too theoretical. He insists the machines go live. Lives change. Historians estimate their breakthrough shortened the war by 2 to 4 years, saving nearly 14 million people. But something deeper happens here. Logic becomes machinery. Steps become algorithms. Human reasoning becomes mechanized. And when the war ends, a new question emerges. If machines can execute logic, who controls the logic they're allowed to run? Chapter 3. Grace Hopper, COBOL, and the Battle for Simplicity. For 3 decades after World War II, the world believed programming belonged to specialists locked inside laboratories and defense contracts. But in 1959, a single meeting inside the Pentagon detonates that belief and launches the most important and bitter language war in computing history. Grace Hopper walks into the conference room carrying a coil of thin wires. 53 years old, Navy Rear Admiral. Sharp, impatient, relentlessly practical. She has spent years arguing that computers should speak something closer to English. Across the table sits IBM's Howard Bromberg, an engineer with a calm voice and a stubborn loyalty to machine-specific languages. He knows IBM earns millions by keeping customers locked into their hardware. A universal language threatens everything. Hopper pulls out a wire exactly 1 foot long. She snaps it onto the table. This, she says, is a nanosecond. It's how far electricity travels in 1/billionth of a second. Executives chuckle. She doesn't. She explains that humans write code too slowly, too painfully, for a digital world racing toward real-time business. Her proposal? COBOL. Common business-oriented language. English-like statements. Hardware-agnostic execution. Software written once, running anywhere. IBM rejects the idea as impossible. Too risky, too disruptive, too dangerous to a $1.2 billion hardware empire. But Hopper refuses to retreat. She pushes, she persuades, and COBOL launches exploding across banks, airlines, governments. It becomes the backbone of global commerce. Yet victory brings a new problem. Chapter 4. Bill Gates, Steve Jobs, and the fight for the user. For a moment in the mid-1970s, the most valuable software in the world fits on a stack of punch cards, sitting on a dusty garage workbench. And the people writing it aren't executives or engineers in lab coats. They're barefoot 20-somethings soldering circuits over pizza boxes. Los Altos, 1976. Steve Jobs paces the garage, eyes burning with a kind of evangelical urgency. Charismatic, volatile, obsessed with harmony between human and machine. On the floor beside him, Steve Wozniak assembles an Apple I board that will ignite a revolution. Built not on hardware power, but on design, clarity, control. Up in Albuquerque, Bill Gates clacks away on a teletype terminal. 19 years old, ruthlessly strategic. He writes contracts with the precision of a scalpel. When hobbyists distribute Microsoft's BASIC without paying, Gates responds with his now famous open letter to hobbyists, accusing them of software theft and redefining software as a product with monetary gravity. Meanwhile, far from both garages, Margaret Hamilton, NASA's lead software engineer, remembers the night an Apollo 11 module overloaded. Her code triaged the crisis automatically, preventing an abort. She coins a new term, software engineering, because the stakes now stretch beyond curiosity or profit. They stretch into space. Assembly gives way to C. C evolves into C++. Sun Microsystems unleashes Java in 1995. Then the web explodes and JavaScript takes the front line. Languages multiply. Markets explode. And something shifts. Hardware stops driving the industry. Software does. Then comes the next transformation, experience. Because once the world moves online, another battlefield emerges. Scale. And a quiet engineer in Switzerland is about to redraw the map of the digital world. Chapter 5. Tim Berners-Lee, Open Source, and the New Rebellion. For 3 years, the most important invention of the modern internet sat on a scrap of paper in a CERN office, completely ignored. No patents, no business plan, no corporate sponsor, just a quiet engineer sketching a future no one believed would matter. CERN, 1989. Tim Berners-Lee stands in front of a whiteboard layered with tangled boxes and arrows. Soft-spoken, idealistic, almost allergic to corporate ownership, he proposes something radical. a universal system where any document on any computer can link to any other. HTTP, HTML, URLs, the foundations of the web. His supervisors glance at the proposal and file it away as vague but exciting. Meanwhile, across the world in Helsinki, a 21-year-old student named Linus Torvalds compiles a kernel on a beige PC. He writes code for fun. He curses bugs with sarcastic precision. He uploads Linux to the internet with a challenge. I'm doing a free operating system, just a hobby. Won't be big. Within months, volunteers swarm in. Contributions multiply. A global movement ignites. By 2001, the movement grows so large that Microsoft labels Linux a cancer, threatening billions in Windows Server revenue. Eric Raymond publishes The Cathedral and the Bazaar, declaring that software built in the open will eventually dominate everything. Berners-Lee refuses to patent the web. Torvalds refuses to lock down Linux. And the world shifts. Software becomes a commons. Code becomes a rebellion. The internet stops belonging to corporations and starts belonging to everyone. But once programming escapes into the open, it mutates. It expands. It accelerates. And soon the network grows so large that humans can't guide it alone, forcing a handful of engineers to chase scale on a planetary level. Chapter 6. Google, Facebook, and the rise of algorithmic power. For a brief moment in the early 2000s, the most influential decisions on the internet were made by fewer than a dozen engineers working in warehouses the size of airplane hangars. And almost no one outside those rooms understood what they were building. Rows of servers hum in a climate-controlled Google data center. 100,000 machines blinking in synchronized rhythm. This is where Jeff Dean, a soft-spoken engineer with a calm intensity, rewrites Google's entire search indexing system in 2 days. Not as a stunt, as a necessity. The world is producing more data than humans can organize. Something has to give. Across the country, in a cramped office in Palo Alto, Mark Zuckerberg pushes code in rapid bursts, socially distant, obsessed with iteration, driven by a belief that connection can be engineered. In 2018, a small tweak to Facebook's ranking system explodes across the globe, amplifying outrage, reshaping political movements, influencing elections. One change, billions of people affected. The old logic of programming collapses under the scale of the web. PageRank calculates authority by analyzing billions of links. Recommendation engines predict what videos you'll watch before you choose them. Behavioral models infer your preferences, your patterns, your fears. Humans write the code, but the code studies humans. It profiles, it predicts, it steers. And in the background, a new transformation is building. One more radical than any before. Because the next generation of systems won't wait for humans to write rules at all. They'll generate their own. Chapter 7. Machine Learning and the End of Explicit Programming. 1 billion images. That's how many pictures researchers need in 2012 to teach a machine something a toddler learns effortlessly. Recognizing a cat. It sounds absurd, but this statistic ignites the moment programming begins to outgrow programmers themselves. Toronto, 2012. Jeffrey Hinton adjusts his glasses in a small lab overflowing with GPUs and humming heat. Soft-spoken, unshakably rebellious. For decades, he believes neural networks, mathematical webs inspired by the brain, can learn patterns no human can write by hand. Most of academia dismisses him. Too slow, too impractical, too weird. But his students build a deep network, feed it millions of YouTube frames, and something astonishing happens. The system identifies a cat without ever being told what a cat is. No rules, no instructions, pure inference. At Stanford, Fei-Fei Li pushes the next frontier. She leads ImageNet, assembling 14 million labeled images because she believes teaching machines to see will unlock genuine understanding. Her dataset becomes the benchmark that accelerates the entire field. The logic flips. Instead of writing precise directions, programmers supply data. Models learn the rules themselves. ChatGPT emerges in 2022. GitHub Copilot rewrites developers' code in 2023. AlphaFold predicts protein structures that eluded scientists for half a century. Machines start generating logic faster than humans can audit it. Power shifts again. From explicit instructions to learned behavior. From craftsmanship to curation. From code as command to code as consequence. And this transformation pushes us to the edge of a new question, one that forces us to confront the future directly. Because if machines learn our patterns, who inherits the world they build next? Chapter 8. The Future Written in Hidden Hands. Geoffrey Hinton once said, "We're creating something we don't yet understand." And after traveling from Ada's ink-stained notes to modern AI labs humming with self-learning models, his warning feels less like speculation and more like the thread tying this entire story together. From Babbage's unfinished engine to Turing's bombs at Bletchley Park, from Grace Hopper snapping a nanosecond on a Pentagon table, to Berners-Lee refusing to patent the web, from Google's planetary scale indexes to neural nets discovering rules no human wrote. Programming has always been shaped by people pushing reality faster than the world can absorb. And when code fails, its impact becomes painfully real. In July 2024, a single flawed update to CrowdStrike's Falcon agent crashes 8.5 million Windows machines across hospitals, airports, banks, governments. Flights grounded, ICU monitors frozen, global outages triggered not by sabotage, but by one buggy software patch. This is the scale we now inhabit. Billions of devices, trillions of signals, zettabytes of data flowing through logic written by teams scattered across continents, and increasingly, by machine learning models trained on oceans of examples. Yet the next chapter stretches beyond today's outages or breakthroughs. Governments race to regulate algorithms. Corporations weaponize data for advantage. Courts debate liability for models that generate their own logic. And AI systems write code faster than humans can review it, raising the question no era before ours had to confront. Who holds responsibility when the author is a machine? But the heart of this story never changes. Programming has always been a mirror of human ambition, our precision, our flaws, our desire to build systems larger than ourselves. Machines now inherit our logic, our assumptions, our blind spots, and they extend them. We didn't just teach machines to follow instructions. We taught them to inherit our dreams and our mistakes. The next chapter is already being written, whether we're ready or not.